Historically, the Grover's algorithm was introduced after Shor's algorithm, the prime factorization algorithm for long numbers. I think 1 or 2 years, after Peter Shor, introduced his algorithm, Grover introduced the search algorithm, and at the time, both of them were working at IBM, and I think they are still at IBM. Grover's algorithm attempts to solve the search problem in an unstructured database. For those of you, who have studied computer science, you must have heard about the needle in a haystack problem. Uh, you have an unstructured database, like you have n, capital N elements in the database, and you are searching a specific entry. Uh, let's denote this with this X, a specific entry in this database. Right? This is called, and this is one of the NP-complete, what we call NP-complete problems. And I'm going to talk about a little more on what we mean by NP-complete problems. But it is, these are hard problems that require, algorithms with exponential complexity. So classically, the expected number of queries, right, on this kind of a database to find a specific entry is on the order of n over 2, right? If you have n entries, the expectation, that you'll find the entry that we are looking for, that we are searching for, you need order n over 2 number of queries. So this is in this notation order n, right? So it scales, but n, capital N, is actually 2 to the n, right? Because again, we are going to map this problem to a quantum circuit, and you have n qubits. So the n qubits can have 2 to the n quantum states, and this is capital N. So this problem scales with capital N, the number of entries in this database. On the other hand, we'll see, that quantum mechanically, the Grover's algorithm requires order squared of n queries. So this is a quadratic speedup. It's not an exponential speedup, but still it's important. I mean, if you assume you have, for instance, 1 million, right, entries in this database, square root of n is 1000. So classically, you would need 1 million queries, but quantum mechanically, you would need 1000 queries. I mean, still, it's quite a bit of improvement. The importance of Grover's algorithm stems, from the fact that the application is very broad. It is applicable to a group of problems that we call NP-complete problems, non-deterministic polynomial complexity problem. And these problems, they represent, in the theory of computation, a class that's exponentially difficult to solve, but once you know the solution, it's very easy to validate. Like for instance, just to give an example, the factorization problem, right? It is exponentially complex, but once you factorize it, right? Once you know the factors of a number, it's very easy to validate. So NP-complete problems are like this. And the traveling salesman problem, for instance, a famous problem, it's an NP-complete problem. The Boolean satisfiability problem, it's an NP-complete problem. And there are thousands of them. And we see this in many many fields in, in many areas of science, in physics, chemistry, math, thousands of problems that we can map to this NP-complete set of problems. So if one of these problems is solved, right, that means all the other problems in this NP-complete set can be solved using the same algorithm. So the generality of Grover's algorithm is due to the fact that it can solve, it can achieve an exponential speed up in this needle in a haystack problem. But at the same time, that means since the needle in a haystack problem is an NP-complete problem, that means you can use this same algorithm with a quadratic speed up on the other NP-complete class problems as well. As I said, there are thousands of such problems. It's hard to solve, exponentially difficult to solve, but once the solution is known, it's easy to verify. So these kind of problems. And one important example of these NP-complete problems is the Boolean satisfiability problem. This, for instance, if you have a Boolean function of x1, x2, x sub n, it's a Boolean function, so that means x sub I are zeros or ones, right? And you have, let's assume a function in this form, x1 or x2 or x3, and x4 or x5 or x6, and another, it's a Boolean function of this form. To find the satisfying set of x1, x2, x sub n of this function is an exponentially hard NP-complete problem. Right? I mean, when we say the satisfying x1, x2, x sub n, we mean the bits string of x sub I that when you plug into this equation, it results is 1. In other words, it satisfies this function. And to solve this kind of a problem, to find the x sub I that satisfies this kind of function is an NP-complete problem. It's a hard problem, but as you see over here, when you know the solution, when you know the x sub I, you just plug in this equation. It's easy to verify, right? Okay, so this is the importance of Grover's algorithm. One might ask the question, can we do better than order square root of n complexity? The answer is no. There's a theorem actually that proves this. It's not very easy to prove, but there's a theorem that shows neither classically nor quantum mechanically there is an algorithm that provides better than square root of n speed up is possible. So this is the best. In other words, Grover's algorithm is able to achieve, the limit, in the best performance as far as the needle in a haystack or NP-complete problems is concerned. Okay. One could formulate this needle in a haystack problem, because in the next part, I'm going to introduce the quantum mechanical solution to this, but we could formally represent this problem as follows. Needle in a haystack problem, or the equivalently any NP-complete problem, could be represented as a function that maps these n entries to a single qubit, right? You have 0, 1 second, and n minus 1 entry, and you map this to a 0 and 1. 1 means success. That's the entry that you are looking for in the database. And all the others, assuming you have only one solution, you are looking for only one entry, you know, in the unstructured database. All the others entries are 0. So this is a mapping from n bits to a single bit. And we denote this solution, in other words, the x, right, that satisfies this f of x equals 1 as x star. You know, that's the solution that we are looking for. That's the solution that satisfies f of x equals 1. In other words, that's the entry, you know, that we are looking for in this unstructured database. I'm saying unstructured because if there's a structure in the database, in the search that we could exploit, then you could do better than this. This limit, the square root of n speed up limit, is only applicable to unstructured database. Otherwise, if there's a structure in the problem, you would be able to develop other algorithms, you know, other ways of attacking the problem that would exploit, you know, this kind of structure. So in this problem now, we assume there's a single solution. This is the hardest case. In general, there may be more than one solution. I mean, there may be more than one entry that we may be searching in the database. Grover's algorithm also addresses this problem. But for now, we'll assume, you know, there is a single entry x star that we are looking for in the database. We are searching in the database.